Teaching a car to react correctly means showing it everything that can happen. World modeling generates these cases, and the system learns to self-correct. Our next speaker, Associate Professor of Westlake University, Kaicheng, with the report, The Generation of the Data Flywheel Concept Through World Modeling for Self-Correcting Autonomous Driving.
Thank you very much. So it's been a great honor to be here. Okay, so today I will present some of our lab's previous work actually regarding self-driving. So I was told that most of here people know about at least machine learning or something, but after this couple of days, I find maybe it's a little better for me to explain, let's say, to take a deep dive to what is self-driving and what are we working on, at least for this directions. Okay, so we give a topic of outlook on next generation generative autonomous closed-loop data flywheel, and I will basically explain line by line what they are and why this is very important to this self-driving community. So a little bit introduction. I mean, this is the outline of my introduction, my presentation, and a little bit introduction of myself. So I did spend some time in Europe before I go back to China. So I studied in Switzerland for my PhD. Before that, I go to Hong Kong University for my bachelor. And after that, I thought it might be interesting to see the opportunities across the world. So I do get some offers from some top-tier United States companies and also maybe some UK companies. And then the time when I make a decision, it's the COVID time. So basically, I then find maybe it's better. I mean, it's both way, right? The first thing is I thought going to China is very interesting to me. Even for me, I born in China, but I literally, like after my high school, I didn't spend time there to actually work for a while. And then I find maybe this is a good time. So after I spend half a year in the US tech company, and then I go back to Alibaba. And then there, I begin my research in autonomous driving industry, actually. So this is rarely known. Alibaba is also doing self-driving for logistics. Actually, it's very similar to the Navi.io, I think, company downstairs. So after a few years in Alibaba, I go to Westlake University for my continue to working on this industry. So essentially, there's a couple of things. I'm also a chair at CVPR and also at Clear. So to work on this industry a little bit more, and also I got some scholarship from Qualcomm company to support my research. Essentially, let's dive into the topic. So what we are actually working on is self-driving. And why self-driving is important, this is kind of like, many people know this, right? Self-driving sometimes can save people's efforts when you're trying to drive. And I'm not sure if any one of you have ever tried self-driving technology, but as personally, when I first time try a self-driving car, and I find even though they are, they fail sometimes, they cannot be, they cannot be really called fully self-driving up to now. But still, when I take my car in the highway, I try to use this technology, and then it actually saves a tremendous amount of time when I, for example, drive from Shanghai to Beijing, for example. It's over 1,000 kilometers, and it's very boring, right? It's on the highway, and people just keep driving. But with this self-driving on, actually, I don't need to pay that much attention to put my foot on the pedal. Instead, I just watch on the road. I just watch what happens on the road, and if there's nothing happens, there's a very good weather, and it's not chaotic. I find it's very interesting and easy to drive after using the technology. But what's the problem of this tech? So essentially, I'm showing on the screen a traditional development mode of self-driving. So first of all, we need to do, we actually working on this, we call this long-tail data scarcity in data-driven machine learning because this is actually true for any machine learning algorithms, even including the large language models. People keep talking about they have the problem of hallucination, right? But hallucination is actually one representation of they are lacking sufficient data to train this algorithm. So essentially, in this case, a traditional development strategy is like the following. People firstly collect kind of like a data for the machine learning to be trained. And then people trying to annotate the data. Essentially, the annotation part is how people can try to teach a computer understand what we want. So this is very important. Second step is called annotation. The third step is, of course, you heard of this everywhere, right? People are trying to buy the high computational cars to train the algorithm. The process of training is very important. And then, before you actually give out the algorithm developed by, for example, some company to every user, we need to test it. So this formula is kind of like a closed loop, and this is also unanimously true across different industry. But in autonomous driving, this is what we can see. Okay. So instead of these three steps, they actually have pretty different difficulties. First is it's kind of like difficult to train the algorithm after you get some really simple baseline models to work. How do you make a better model? Especially when you have many new collecting data every day, right? Because if you have, for example, 1 million cars on the road like Tesla did, and then you have actually collecting data every day, and how do you make this data work? And the second thing is, how do you afford a high kind of like efficient data annotation to teach the algorithms? This is also very important, right? Because manually doing them is very expensive. One people can spend like minutes to only labeling one 3D box, for example, a 3D location of a car. This is not easy, actually. Even for a human being, for us, if you are not specifically trained for it, it might take even half an hour to provide a very fine-grained labeling for one. And also, when you're trying to train, this is even harder. First of all, because the cars are very expensive. They are pretty expensive because everyone is trying to use it, so this cost is tremendous. And also, you need to maintain this every time when you have new data. So this is also what we call the training algorithm. And the finally is simulation is also very hard because you know that this autonomous driving, on the good hand, is it can save people's effort. On the other hand, it can kill people, right? If you're doing this incorrectly, and actually can kill someone who are driving normally. So there are a couple of accidents happens across the world. I'm not going to mention it, but this actually emphasize how important it is we should treat this technology. So essentially, to solve the problem, we actually, as me or the lab, in the last few years, we are tackling the three major parts in three aspects. The first one is we're trying to find a good way, try to train the algorithm with less efforts, at least less human efforts. The second thing is we are trying to make use of the largely collected data and try to find a way automatically to give a label to them. And especially when you have LiDAR sensor and also the camera sensors. Another one is we're trying to deal with the really long-tail data scarcity problem, which means that this scenarios is something you never see, but still we are managed to make some new cases out of the old stories, okay? So essentially we are trying to solve this problem in three aspects. And essentially, the lab's research can be summarized in this following figure. Okay, so basically, we cover, except for now, the development and testing. We try to solve the problem with hyper training algorithm, assign the automatic annotations, especially with multi-sensor. When you have multi-sensors, you will have alignment issues, and that's a big problem when you have different sensors. Okay, and then we are trying to solve the problem from the beginning. If you are not even able to collect such data, how do you deal with it? So essentially, the first line of research we're trying to do is we called neural architecture search. So neural architecture search is something in this domain trying to solve a problem of how to design an algorithm. So this is very similar to Professor Tian Ye's talk. Okay, so he's trying to make AI automatically design AI, and this happened to be my PhD research. So this is what the first thing we're trying to do. So essentially, the motivation is pretty simple as well. So instead of trying to train the algorithm, design the algorithm by, let's say, hiring a very knowledgeable machine learning engineer, instead, we can try to formulate certain rules and algorithms to make it work. So the first thing, but the problem is, when we did this research in like 2020, around 2020, and we find that the most state-of-the-art research on the world is no better than a random search, which is the simplest thing you can even think of, right? Just rolling a dice. That's the if you compare to the algorithm back then, so finding a good algorithm is similar as running a dice. This sounds not very good, right? So essentially, in this research, we try to do two things. The first thing is we identify this problem, especially with a careful design framework. And the second thing is we propose an anchor-constrained neural architecture search strategy to solve the problem. So essentially, we improve this algorithm's performance by 5%. And also, when we try to deploy this technology inside Alibaba's internal product, we actually gave a boost of 97% of the performance, especially when you interact with the algorithms. So essentially, actually, this is funny thing is when we present these results to LeCun, and when the LeCun is not a Turing Award winner back then, and actually he thought it's pretty interesting. And also with these achievements, we also get the acknowledgement of the Quantum Innovation Fellowship in Europe. And then the more interesting thing is when we deploy this algorithm inside Alibaba, we actually find it, before we try to train an algorithm, there are, roughly speaking, 150 steps an engineer should follow through the process. It lasts over 3 months. And after we do this, and actually we find a way, most of them are engineering work, of course, but they cannot survive without the scientific inspect inside. But after we develop this, and people only take 7 steps to finish the retraining of one algorithm, and which is very important to the efficiency of a company. So the second thing is, when you try to, the first rationale is, when you have the same amount of the data, you want to squeeze the most of the algorithm. But after you have it, how do you solve the problem of, we have many unlabeled data? How do we deal with this unlabeled data? So this is essentially, we are giving a summarization of this data, are widely collected unlabeled data, and how we can make use of it. And we can make use of it with 2 ways. Maybe some of you, if you are familiar with machine learning, there is a way of semi-supervised or unsupervised learning, which you don't really need a label. But essentially, when you look back in the industry, even for the large language models training or for the 3D scene training, the labels are the most important thing to the world. That's why people have, for example, Scale.ai, that's a very big company, only targeting for this, what we call data annotations, right? So essentially, this is important, but what's the problem we are facing? The problem is Tesla already built an auto-labeling system, which is very good, working very well. However, this is not the case that when you have multiple sensors installed on your vehicle. For example, of course, this is a debate. There is always a debate that pure vision versus multiple sensors, but at least when there is no one trying to say that when you have LiDAR, you have disadvantages, because the LiDAR is what we call proactive sensing, right? You are shooting out the laser to a point, to the objects, so that even though the camera doesn't work, camera is passive, taking inside the light signals, right? So these 2 signals, they are quite different in principle. So at least doing this is important. This is what we have a consensus inside Alibaba. So in this case, we find out actually there is a problem when we do this in real life. First of all, when the time 2022, when we are trying to develop these algorithms, every algorithm running on Earth, for example, trying to do this fusion algorithm is always starting from a LiDAR point. Either you take the LiDAR point, do some kind of projection to your camera, get some features from the camera space, and then merge it together, or they are just trying to use a transformer, trying to correlate some camera features to the LiDAR point. Doing this is fine when you have a perfect sensing. If you have, for example, 360 degrees LiDAR points, that's very good, because you have every corner covered by the camera and also by the LiDAR. However, most of the cars, as you might see some cars in the current, the road on the road now, they only have a forward sensing LiDAR with a round, with everything else is camera sensor. How do you deal with this? We find out that back to 2022, the algorithm trying to do the sensor fusion fail miserably if you don't have a LiDAR point. So in this case, we develop a new algorithm. So first of all, we identify this problem. And the second thing is we develop a very simple but effective algorithm called BV Fusion. And BV Fusion just changed the problem by separating. Okay, we separate the LiDAR feature extraction and also the camera feature extraction, so to achieve a point that both sensor fusion actually helps each other rather than decreasing the performance of each other. So in this case, we actually find out that by doing the simple thing, we improve magically the performance over 127 from, I think, around 5% to something 30 to 40% accuracy, if I can say so. They have a specific name, but accuracy is good to capture it. So by doing this, we also notice another interesting thing is we should not use actually depths to measure the distance when we talk about autonomous driving. Because depth can vary, right? If you, for example, predict a depth of a car that is 2 meters away from you versus predicting a car's distance over 140 meters from you, the difference between 2 meters and 3 meters appears pretty big if you care more about the local density. However, because if you know that when you are changing a very small angle from the very short distance to a long distance, if you change the angle of the prediction by 1 degree, if you are at 140 meters long, maybe the difference is like 20 to 30 meters away. So this is pretty bad. We actually discovered this. There is more efficient algorithm for let's say feature extraction by doing the height. Instead of using depths, we should measure the distance between the point to the car versus to the ground, because every car on the road is only 2 to 3 meters high. So essentially, by doing this, we improve the robustness by a large margin, and this seems to be very effective, especially when you put the cameras on the truck, for example, especially maybe even higher on the road camera. This works even better. So essentially, with this technology, we also try to solve the problem of the robustness. And by doing so, essentially both algorithms, no matter BEV Fusion and BEV Height, are officially included in NVIDIA's official repo for the autonomous driving. And also, we think this is a pretty big acknowledgement as NVIDIA is trying to provide the most efficient algorithm to the world. And also, when we deploy this algorithm, the auto-labeling system inside Alibaba, we find that actually the 3 annotation fees for a box reduce from 1.4 RMB to only 0.13 RMB, which is over 90%, saving tens of millions actually RMB for the annotation budget internally. So this is a pretty important aspects of the advance in this field. And also BEV Fusion now is also quite, this is pretty safe to say that everyone is using BEV Fusion if you are trying to deal with LiDAR and camera for the same time. So essentially we find out 2 things, right? The first thing is if you have the fixed amount of data, try to get a better model. The second thing is if you have the way to annotate more data, the performance is always going better. But what happens realistically, actually, so after the 2 steps, this is only the beginner lessons of autonomous driving because everyone can do it. However, after the 3rd step, this is really enter a corner. What do you mean by corner? The corner just means that the case you've seen is rarely happening. For example, there is even an extreme case that one autonomous driving vehicles recorded a plane landing on the US highway. So this is something you might never imagine in your life, right? A plane just landed in front of you. I mean, as a human being, we know what a plane is, and this is very dangerous. We shouldn't crash on it. But for a machine learning system, if it's the first time seeing this scenario, it's very likely that they will not understand and just crash it. So essentially, the point is, how do we make such case even better to try to do the data balancing issue? Another thing is, as I mentioned, this corner cases rarely happens. They only happen probably 1 over a million times. However, if you are, if you know about the machine learning training algorithm, there is a phenomenon called, let's say, data balancing issue. What is data balancing? Balancing means that if you throw one case into a million, for example, normal cases, it is very unlikely the machine learning algorithm will remember the one case you throw to the system. It's like you throw a stone to the Pacific Ocean, right? There will nothing will happen. So in this case, if we cannot find the sufficient way to enlarge this data portion, for example, at least to maybe 10 to 100, I mean, there is likely to be no chance that you're training the algorithm, you alter the algorithm by only one case. So this is the third thing we notice inside the company and also move to the university trying to do is when you don't have much collected data, try to make them. So essentially, the rationale behind this data algorithm is what we call the neural field. Okay, so this is a special term, implicit neural fields. So let me just briefly explain this. Before people have this technology, what people are trying to do, they are making a game. So I mean, even inside autonomous driving, this is not a joke. Even inside autonomous company, people, when you try to make 3D data, the best way is you construct a similar environment like a game. Maybe some Unreal Engine, maybe something else. You do a 3D simulation. You buy or create some assets, like a car, like a pedestrian. You stack into that simulated 3D world, and you using the simulated 3D world to solve your data generation problem. But actually, the pain is the 3D world drastically differs than the real world captured by a camera. There are many, many things. I'm not going to go over them one by one, but there are many things that are different so that there is always a big gap. But implicit random neural field actually solve the problem by providing a different solution. They are trying to use the real data, train a machine learning algorithm, predicts what's the underlying features embedded in a camera, rather than using a fixed parameterized 3D camera model like in a 3D engine. So in this case, people discover that actually we can try to really generate high fidelity sensor simulation by doing this. But the problem is people only do this for camera. There's no one doing this for radar, okay? So for the LiDAR or even radar. So this is our work. We are one of the 3 groups actually in the world developed this 3D LiDAR rendering by using implicit field, and also we generalize this to a double fidelity. We're doing this for LiDAR and for camera at the same time. And again, the alignment is an issue. So when we do this, the merging, the fusion work, actually people finds out, the different modality hurts each other. You only find algorithm on the world maybe make LiDAR better, but the camera worse, or vice versa. This is not very good, at least to us. So essentially, we try to solve the problem by generating this in the new algorithm, and we managed to, for the first time, actually make both modality improve in the same implicit field, in the same 3D representation. And also with the same core technology, we moved it to diffusion fields and trying to do a generative work. And this work actually wins the ECCV challenge for the first place and in the previous time. And also, this technology underlying, we partnered this with Li Auto. Maybe Li Auto is pretty famous in Russia. I see many of them in here. It's also very famous in China. And we actually do partner with them to trying to serve their serve in their data engine realistically in their industry, try to solve the corner case problem. So essentially, up to now, we actually finished this. We tackled the problem of closed loop data flywheel to solve this long-tail problem in 3 aspects. Firstly, we deal with when you have the same amount of data, but try to squeeze the best from the model. The second thing is we try to do auto-labeling. The third thing is we are making some new data to solve some rarely seen cases so that people can, being protected from the autonomous driving technology, I would say. So, but what's next? So next is generative world modeling. So this world modeling is very, very popular recently, especially by Fei Li. Okay, so Fei Li is advertising this concept a lot in the US, and also there are a couple of counterparts. But I'm going to provide a little bit, perspective from my side why this is important, especially in the autonomous driving industry. So as I mentioned, we mentioned over 4 in the first part of the presentation, right? We mentioned about how to train, how to make more, annotate more data, and how to make some new data out of nowhere. But we didn't mention the last part, which is testing. And testing is very difficult to do. Traditionally speaking, I'm not sure if you're not in this industry, you might not know, but when we work in the industry, we actually need, when you're trying to do some real testing, you need to actually, for example, find a highway that no one it's not a very popular highway, and then you pay a large money to rent this highway. You block the highway for example, 1 or 2 days for like $500,000 in China. And then you drive your cars there. try to find the realistic testing for your vehicle if you are not familiar with some cases, right? This is the ground truth we call. This is the truth we can rely on because everything is the same, right? You have the same road, you have the same car, and you have some audience, you have some model cars that your employee is driving to run around to simulate some dangerous situations. And this is real, but this is very costly. I remember the days when we do this. Actually, I'm part of the fleet. I'm trying to drive a car, cutting the truck. First of all, this is very dangerous, even for me, for the company's employee, right? And the second thing is this is very inefficient. But the problem is, if you have no better ways to test your algorithms, how do you do? You can only do this, right? The second thing is we can only try to test a very tiny fraction of the rules we have, but these materials are coming from Chinese traffic laws, but I assume everyone on the earth have a very complex traffic and also comprehensive traffic rules. And essentially, how do you test each rules one by one in the realistic scenarios? Literally, there's no way, right? Otherwise, even if you are a car company of autonomous driving that have 1 million cars on the road, maybe you by luck running all of the cases. But still, what happens if rules are trying to stack to each other? And the second thing is the traditional third-party simulation is very easy to hack. As I mentioned earlier, right? This is a very simple case that you can hire a road or build a simulation, for example, play yard for the autonomous driving vehicles. However, machine learning is doing the best thing machine learning can do is memorizing. And if you have only one play yard, it's maybe for the first time it will fail, but after a couple of seconds, it will just succeed without problems. So essentially, this is the problem we're facing, right? How do we trying to solve the testing problem by doing this? So essentially, this is one video I recorded on my own car in China, and you can see this is a pretty complex junction road, and then we have, maybe this is not in Russia, but in China we have this dash lines, which when you are waiting the red light for very large junctions, you can move ahead instead of waiting behind, okay, just to make it more efficient. And there is actually a policeman there trying to coordinate everything, and there are many, let's say, cycler trying to ride this little bike, and also you have many words on the screen. You can see that there is a road sign. There is also road signs with words. This is also very common. But how autonomous driving system understand the composition of everything? So this is essentially the complex road structure, complex interactions, and also traditional this testing block is just insufficient to solve these combinatorial problems. So essentially, this is also why we see the industry have a development of the autonomous driving technology from the rule-based. In the beginning, in 2012, for example, people are trying to use the rule-driven approaches. For example, right, if you see a red light, stop, something like this. This is very simple, yet works. But it doesn't work when it's getting pretty complex. People gradually move from this rule-driven to what we call divide and conquer-driven, and then gradually to this end-to-end, which you actually put all the data to the same model, trying to learn. And now we even have this what we call the vision language action. This is another version of a large language model. Instead of trying to put the language, you also put images and also actions into this model. Okay, so this is a counterpart of language models, and then some new technology maybe in the future. But the process of doing this, upgrade is not for fanciness. It's more like because the number of the scenarios you are dealing is getting more and more complex, trying to use traditional approaches to solve the problem is going to be impossible. So what happens is now is we might encounter some cases that are written in the traffic rules, but you never collect it on the road. How do you do? So essentially, our solution is we are trying to use a generative data model, try to serve as the traditional, because traditionally speaking, there are many research in the world, especially in the transportation side. They work on how to decipher a traffic rule. They work on how to generate some traffic rules, traffic scenarios. But if I may say so, they are just little blocks on the screen. Okay, so if you have a car here, instead of you really see the car, you said, okay, this is a block. So this is what people have tried to do before. And what people are trying to do now, especially for this, what we call end-to-end, or this recently, if you see Tesla, if you see the auto, everyone is not doing this little block by block. It's more or less, you just see the driving scenarios, and then they predict the results. But this is insufficient there is a gap between these two, and the generative model modeling is just the middle part, the middle layer, trying to solve the problem. So essentially, in essence, we're trying to generate a new scene to solve the issue by doing the generative modeling. And these are a couple of examples we can see. So everything here are purely generated. So nothing is really filmed from the road, okay? So you can see that it looks pretty same as what you can see. And this is, we use this as a case because it's a wide region, it's a large chaining, and on a very wide junction road, so to see the performance. And also we can provide this kind of like control. We can try to draw this road, and this is also a demo case. You can draw the road freely, and then you can render a scene correspondingly with the very accurate 3D aspects. And more importantly is we use these two technology, combining them to build a self-correcting autonomous driving algorithm system. So this is what we call self-correcting self-driving system. And here, actually, this paper is recently admitted by this III, which is one top-tier conference across the world for AI. And we actually managed to drop 39% of the failure cases automatically by generating some new cases. This basically evidenced the effectiveness of this approach. And also, more interestingly, in the future, and this is something ongoing, we are trying to do generating a more complex roads, for example, different traffic signs, different kind of junction roads. I mean, these are all in China. Maybe you don't see them, but you can see that there are little big cross on the road. This is just to indicate this is a dangerous area, for example, and also control the traffic lights. So this is basically, in essence, we try to make the world model know more about the rules, okay? And the second thing is we are trying to unify the generation and understanding, because generation and understanding is a very interesting topic nowadays, as our group always do. We are trying to unify these two basically different approaches into one, so that in the future we can be more efficient, and also generation also being helped by understanding problem. Another one is we also try to design a more interesting end-to-end driving algorithms with the previous research foundations. And essentially, this also can be used as a reward for reinforcement learning, which is also very important. If you notice in this field, people basically are running the vision language action models with the reinforcement learning to help it being better, to be more, human-like, for example, in this field. So essentially, we are also capable of doing this. And essentially, we are trying to do the same thing again for the humanoid as well, because everything in the humanoid is quite similar as the self-driving. I mean, in China, we have a saying that embodied AI, but embodied AI actually is a very broad definition, and it covers humanoid, it covers tripod, it also covers autonomous driving for navigation problems, right? So essentially, we also try the same thing, and also works on the humanoid, at least. We observe a roughly 40 to 50% rate of succession just by generating some new data without any hurt. So essentially, we basically just conclude of what my research is, and I'm just use last couple of minutes to introduce our university. So first of all, we want to thank all the industry supporters and also academic supporters of our lab. We have many collaborations, especially with Xiaomi, with Li Auto, and this is some companies in China which are working specifically for autonomous driving. And also, university is here, so it's a newly founded university which are specifically for research, and we are pretty proud to say that they actually are very unique, even in China or across the world. So we try to be more international. So if you have anything, you can try to reach out to me. And also, to be summarized, we just trying to deal with the autonomous driving problem, the corner cases problem, gradually. Firstly, by training model efficiently. Second is labeling this unlabeled data. Third is trying to make some new scene based on already existing ones. And lastly is trying to create the scenes that you never seen even in the training data by doing the composition. Okay, so this is what we do. And last but not least, we want to thank the team, and also we are hiring. So if you have anyone who are interested in us, please consider joining us. Okay, so that would be all. Thank you very much.
Thank you, Professor Kaicheng Yu. Thank you for sharing your experience with us. Enjoy Russia, enjoy Moscow, enjoy the conference.
Thank you.
Thank you.